larger, older crater and the new. So this one is, you're looking at the Marcy weather camera. You see how bad resolution. We zoom into this. That box zooms in here, and then we can see the color, higher resolution image here from Cassis, and we can zoom even further. Impacts cause Marsquakes through the seismic vibrations. Once the impact hits the surface of Mars, it radiates seismic waves, and those seismic waves propagate through the layers of the interior of Mars to arrive at a seismic station. And we had one seismic station so far on Mars, the InSight lander, which landed in 2018.
3, 2, 1, 0. The liftoff of the Atlas V, launching the first interplanetary mission from the West Coast, and NASA's InSight, the first outer space robotic explorer to study the interior of Mars.
Might be against the stops. I couldn't actually check whether that was the case. Now, how far are we in terms of? If I focus it, this is a part of the spring. No, this is the spring. Okay, so that's actually one of the wires. If I go out a bit.
In fact, we're finding out that through the detection of an impact that we were able to definitively associate with the Marsquake, that the seismic waves are able to take a faster path or a highway, let's say, through deeper layers of the planet, the mantle, and arrive quicker at the seismic station and still be located further away.
No, if you keep it on the X, the Y takes it away, so that's definitely safer. That has taken a bash or two. That should be a rectangle, and you can see it's not quite. It's got a little bit of a kink in it.
Almost like a zigzag.
Yeah. So, how are we doing? These meteorite hits have a lot of higher frequencies in the signal, which means that previously we were kind of seeing the planet in black and white. Now we're seeing it more in color. We're seeing it deeper. We've got a full spectrum of seismic signatures coming in, and this means that we can understand a lot more about the interior of another planet.
And here in our study, we focus within a 3,000 kilometer radius around the InSight lander. That will cover about the area of 3 times that of Europe. And to search throughout the thousands of images that we have would simply take a human years to scan at the detail that the AI could have done it. And this is why we used AI to scan throughout all these, I think exactly about more than 120,000 images. Each is about 30 kilometers wide, each of these images, and identify for us potential candidates that are blast zones from new, fresh impacts. They're somewhere here, and impact is there.
Yeah. pretty near to the equator. Yeah. So essentially, what big data poses, I think, to just about any problem, is that you have a haystack and you need to find the needle. So you've got that large amount of data, more than actually a human can literally comprehend. So you've got to take a new approach. And this is where AI comes in. This is where AI and machine learning, being able to mechanize a way that a human looks at it. So we take, if you like, the black box of the human brain, and we translate that to the black box of AI, and then out from that pops where we need to take a second look. And so it doesn't necessarily give us the definitive answer, and anyone who uses AI knows you've got to be very careful when you get an answer out of that to check if it's right. So we get what are the most likely solutions, we take those, and then we concentrate our fire on that, including taking more images.
What we are finding in our study is that the meteorites appear to be hitting Mars almost twice as often as we previously thought through other orbital imaging surveys. And there's definitely a lot of Marsquakes that are impacts in the catalog that we have detected with the InSight. And all of this will help us understand the interior structure of the planet. And because the interior structure is a time capsule. And as the seismic waves probe through that time capsule, they can help us understand the origin, the formation, and evolution and current state of the planet, and how other rocky planets may have been formed and evolved.
Now we're producing something much smaller, and we're measuring it electronically as to how it's moving.
Right.
And instead of, this is basically a mass on a spring. So what you're looking at is when you have a vibration, the mass moves around. And we have such accuracy now, we can detect if this moves by a fraction of an atomic space. They would have been really nervous. But
It's so sensitive, in itself.
So it's going on to the moon. Mm-hmm. So we've got it going up September next year. Mm-hmm. We've got NASA funding to make a version of this to go to Venus, 500 degrees Celsius, which is kind of a challenge. So that's going in. So real engineering happening. Check that that's not going to fall out. Okay.